Good morning, good afternoon, and good evening, and welcome to the Friday Talk Show with your host Rajiv Kulkarni. Today's date is 7th of August 2026, and right now the time is 9 a.m. Central Standard Time of United States, which is 7:30 p.m. in the Indian Standard Time in the evening, which is a Friday. Happy weekend to you, and let's get started on the show today. And we have our veteran electronics expert, technology expert, design expert, and also he is the current president of Surface Mount Technology Association of Indian chapter, Mr. Ambaprasad, carrying more than 40 years of experience in the design front and working in the electronics manufacturing industry. And Global Electronics' main purpose to bring every Friday this talk show is basically to create awareness and to bring the wealth of knowledge that our veteran speakers they have in their particular field. You're also welcome to participate with any new topic that you have. And currently we are carrying the 8th episode of a series of topic and which have been going on for the last 8 weeks, I would say. But in between, we have a couple of conflicts we had because of my travel activities, which conflicted with the timing. So at that point of time, either I redo the repeat show, or I will not do the show. Anyway, sorry for the inconvenience that gets caused, but let's welcome Mr. Amba Prasad. Good evening, Mr. Amba Prasad. How are you this evening?
Doing good.
Great, great. So let's get started, and I will start presenting the screen, and then you can then take over. Okay. So here we are.
One slide backwards. That's enough.
I think this should be good.
Yeah,
Yeah, it's a full size.
Yeah. Full size?
Yeah, it is full size.
Okay. First of all, tell me the voice is clear. I did some setting change.
Yeah. Yes, okay. Yes, your voice is clear. Yeah.
Last episode, we closed at the package to board. Package to board. How we do the routing from the package to the board. And we talked about the evolution from 2.2D to 5.5D. Up to 5.5D, according to IEEE, packages are available. That maybe we can cover a little later. What is 5.5, what is 4, what is 3 and all. But these are the options. This is the physical architecture of a package. And here, though we talk about high-speed I/O interface, which is mostly SerDes and sometimes parallel bus, power supply distribution network plays a very important role. So in this episode, we will be covering that. Most likely next episode also, we will carry over from this to this. With that power supply distribution, I will be closing. Go to next page, please.
Physics-based interface routing chip level interfaces. Role of a robust PDN in HSIO PCBs.
Just 1 minute. Yes. I have aptly named it role of robust PDN in high-speed I/O PCBs. Go to next page. Agenda, rack to chip PDN distribution. Some of this we covered previously. Board level power distribution network frequency mapping. This people know this is almost 30-35 years old sort of an algorithm. A package level PDN map, which is sort of new. Impact of PDN, power distribution network stability on high-speed I/O board functionality, and depletion wave. What is depletion wave? I will just explain. Next page, please.
Wow.
Yeah, this is the picture. Though I took roughly a data center as a reference, this can happen even in telecom or even a server. we are telling 48. Right now, I'm sticking to 48 volts DC because that's what we used in telecom. I did most of my boards in telecom only. I stuck to that. And then they can be, PCBs can be vertically mounted or servers can be horizontally mounted. The picture is available at the middle. And then it goes to the actual package. I'm showing a PC, the rack, the PCB, what they called as a card cage or a guide, whatever it is. And then we are looking at the actual package at the extreme right. Ultra low voltage, what happens though we give minus 48 volts DC, your chip will be consuming sometimes zero 0.8 volts for core and at the maximum 3.3 volts for IO. And again,
Hmm.
a lot of interfaces will have their own level of voltages. Though we have 3 volts in as an IO, a particular IO section of IO can have a separate 3.3 volts. Some other section have same 3.3 volts derived through some other voltage regulator. They keep giving them different names, but ground is common. That's the case. Next page, please. Impact of PDN on HSIO board functionality. I thought of putting performance. Rather than performance, I thought functionality makes a better understanding. During switching events from SerDes lanes, without PDN resilience, supply droop translates directly into timing jitter. In fact, it is called as power supply induced jitter. Bit error ratio and IO functionality. And the power distribution network is a critical as signal channel themselves. Though we do simulation for the SerDes channels, sometimes people take power for granted and they don't give as much as importance for that, but it is equally critical. Going forward, I will show how it is as critical as the signal length matching or whatever the budgets we have, etc., etc. A robust PDN ensures the core voltage rails remain stable under massive correlated degradation and eye closure, undermining the entire signal integrity budget. A robust PDN is equal to stability under stress. Stress can be fluctuation in power, fluctuation in timing of the signals, as well as thermal. Thermal plays a very key role over here. In fact, thermal induces sort of a non-performance in power PDN, and the PDN, if not functioning properly, will give rise to thermal. This is cyclic. This goes on and on and on and on and on till the entire PCB or the package fails. It provides a low impedance across the wide frequency band, 100 kilohertz up to 2 gigahertz, ensuring the transient currents are supplied locally without propagating the droop. Budget protection by holding droop within the ripple budget. Example, less than or equal to 20 millivolts on a 1.volt rails. This is just an example. The numbers may vary. The PDN prevents a supply-induced jitter from consuming to a tight, high-speed IO margin. Next page, please. Again, role of a robust PDN, voltage stability, maintains rail voltage within 2 to 3% tolerance under correlated switching. When we designed boards, say even 15 years back, 10 to 8% was normal, but now it is 2 to 3% is the margin. Noise suppression keeps the PDN impedance below target less than 1 to 2 milliohms for 1 volt rail or a sub 1 volt rail at 16 to 32 amperes of transients. Signal integrity protection prevents a supply-induced ditcher from consuming HSIO eye margin. The eye closure will not happen. Eye will be wide open. Reliability reduces EMI, thermal stress, and component failure risk. This thermal stress I told earlier, the previous slide. The thermal has got a direct impact on PDN, and the PDN has got a direct impact on thermal. These two are very cyclic. That's why when we do the simulation, it has to be a multi-physics simulation. Next page, please. Impact of PDN on HSIO board functionality, power integrity, budget. Now, I did some Wikipedia search yesterday. Budget has got two meanings. Budget means which is something very cheap. We say budget watches, budget cars, budget travel, budget airlines and all, which is below market price. Or budget means you plan for certain things. You don't go between min and max. So
Correct.
budget has got two meanings. So sometimes budget means cheap also. Here what I mean in budget is it is well within the tolerance, well within the planning. What we planned in the simulation, what we planned in product design kit, that is met. Budget element, ripple budget less than 20 millivolts, 2%. Local droop can exceed 30 millivolts according to depletion wave. What is depletion wave we'll be covering in the next episode. Mitigation, tight capacitor replacement and stitching wires. Stitching wires can be for ground also, and stitching wires can be for the power also. PDN impedance less than 1.25 milliohms, 100 kilohertz, 2 gigahertz, the frequency range. Anti-resonance peaks greater than 2 milliohms, mix of capacitor values. This is a 30-year-old technology. People used to put a different value of capacitors as a plan B to mitigate the frequency response. Because beyond a cutoff frequency, the capacitor acts like an inductor. It is not doing of a capacitor. Local droop less than 15 millivolts at package pins. Okay, and it should not get inside the chip, inside the package. The package to chip, there can be a wire bonding or TSVs or anything else. It should not go there. Hotspots near SerDes clusters. This is the last slide what we showed in the previous episode. Suddenly you find lot of, when you do PDN analysis, we see a lot of red spots near the pinouts, especially near connector pinout as well as near the chip pinout. On package plus PCB high frequency caps. Now the capacitors, so far people kept only on the board, but capacitors can be there within the package and capacitors can be within the chip also. So this is the meaning. And a capacitor can be a tightly coupled supply to ground parallel plane also. So these are the options. Voltage regulator module transient less than 10 millivolts step response. VRM lag amplifies droop. Multi-phase VRM low ESL package caps. So these are the mitigation. Next page, please. This is a 30-year-old diagram. People thrived on this. This no longer holds good, but still to carry the legacy, I'm keeping it here. So we have a voltage regulator module, and then there's a power entry. There we put all what we call as a Coca-Cola can or a Pepsi can, aluminum capacitors we put, very slow response. That operates at a kilohertz frequency. Then electrolytic capacitors we put in the megahertz range. Then there can be wires, then medium frequency capacitors, 10 microfarad, 1 microfarad ceramic, and these values is a typical value. The value can change according to process design kit. And there are three capacitors we have put yellow color. In the middle, you can see a reverse geometry capacitor. The capacitor is tall. So you can see the leads are also quite wide. So this is a reverse geometry capacitor. For example, 0603 can be 0306 because you get a bulkier lead. The inductance will be less. Then high frequency capacitors, 0.1 microfarad, 0.01 ceramic in the package. Okay. And then within the package also, they can be on the die capacitors. This is the just, and below how it bulk caps their range, it has been given. And then we have given low frequency DC to 1 megahertz, medium frequency 1 megahertz to 100 megahertz, and high frequency to greater than 100 megahertz to gigahertz range. So this is the operation. And wherever you are seeing some sort of a spring type of a coil, that is inductance. So beyond certain range, the capacitor will act like an inductor. So on the capacitor, this is a very 30-year-old picture. Nothing much has changed. People still thrive on this. I think with this we can take a break.
Okay.
And then we'll continue the others.
Okay, sounds good. Okay, good afternoon, good morning, good evening to all the audience out there who are watching our show and supporting our channel on a regular basis. Every Friday, we bring this show to share our wealth of knowledge in the electronics manufacturing. And please do subscribe to our channel so that we can grow further and we can bring more and more speakers with different topics. So let's take a quick break and watch this video and come back. Good morning, good afternoon, and good evening, and welcome back to the Global Electronics Friday Talk Show with your host Rajiv Kulkarni. Every Friday, we bring in this talk show, to discuss about various topics in the electronics manufacturing, whether it's a design, whether it's a supply chain, whether it's a trend in the electronics marketing, sales, as well as the manufacturing activities. In the manufacturing, we have the process engineering, we have quality aspects, and then so many various topics that gets engaged in the electronics manufacturing. So if you are interested to be a part of our talk show, please do reach out to us, and we will be very happy to work with you and work on your topic of interest. So let's continue our today's topic, and we have Mr. Ambaprasad, the technology expert with more than 4 decades of experience in the electronics design and manufacturing activities. He's based out in Silicon Valley of India, which is Bangalore city in the southern part of India. Let's welcome back him. Mr. Ambaprasad, welcome back to the show after this small break, and let's continue our discussion. And here you go. I'm going to present share the screen again, and so that you can take over further on this. Here you go.
Okay, be in the same screen. Be in
Yeah.
the same screen. No issue. This screen we may reuse, or we may make a better image than this to show how the same this algorithm what we used 30 years back is a best line of defense against a depletion wave. In the next episode we do. If I don't get a better picture better than this, I may reuse this. Apologies for that, but I hope I'll get a better picture. No problem, because the technology is changing so fast. I can generate a new one, absolutely no problem. So don't assume that we are copy pasting. Yeah, that's one advanced set of notification I'm giving. Let's go to the next page, please. Impact of PDN on HSIO board functionality, same subtopic. Design and mitigation strategies, hierarchical decoupling, bulk mid frequency or written midband. It is bulk low frequency, midband, and high frequency on package capacitors on package. So this midband may sit on the PCB, but on package it will be within the package. So we don't have much say on that. Power plant design, tight spacing less than 0.2 mm, stitched reference vias, continuous planes. This is the via stitching and the power plant stitching if required sometimes. Many times I have done many boards previously where even core voltage we had a two parallel planes. One plane was not sufficient actually. So two. So if you have a two planes, better we stitch it. Decoupling capacitor distribution, spread values, so 10 microfarad, 1 microfarad, 100 nanofarad, 10 nanofarad to flatten impedance curve. The watt curve we saw 3 slides back. These are typical values, but values may change. Dampening RC networks for lossy ferrites to suppress anti-resonance. Some companies don't use ferrites. Some companies use ferrites, depending on the company philosophy. It's just a recommendation. VRM core design, multi-phase regulators with the fast transient response. So this is again, we can buy the VRM modules, or a company has got good resources, they can design themselves. But I think buying is a better option. Next page, please. So this is how your board looks like. If you are using in a server class board, system power supply, it can be minus 48 volts or 12 volts at the entrance. Then you have a voltage regulator module, mostly near the edge connector. Then you have aluminum capacitors. Then you can have bulk capacitors, really bulky. Then you have high capacitance multilayer ceramic capacitors, then power plane and the PCB. So one advice here, lot of tantalum and niobium capacitors which are mid-frequency, after certain time, certain age, they lose their performance. So generally what companies do is they replace them. This has happened. This was happening even 20, 25 years back. Even now people do it. Okay. Then I have shown the frequency curve over here. Then there can be GPU, PCB, MLCCs 0402, 0201, 01005. These are the capacitor sizes. 0402 is 1 mm by 0.5 mm. 0201 is 0.5 by 0.25. And 01005 is 0.25 by 0.12 mm. That is the capacitor size. Surface Mount Technology Association has got a greater role to play over here. So these capacitors, yeah, this is very much important. So this has to be done. And main PCB decoupling, mid-frequency decoupling, then 3 reduced loop inductance. This is generally done by the pin assignment when we buy the package. We don't have a PCB designers much have a scope on this. In-package decoupling, there can be decoupling within the package also. Then you have IO pins, deep trench silicon capacitor. This is a new technology. You can see a capacitor is put within the package. The capacitor looks like some sort of a vertically it is mounted like a cylinder between power and ground, you can see. Chip level and on the die decoupling, ultra high frequency decoupling, vital for local switching noise. When I go to depletion wave, I explain how these capacitors will play a major role. Then that's it. M1, M2, M2, Mn. These are all connections. Next page, please. This is how a package looks like. Given a PDN budget, a pyramid I have shown, bulk decoupling, then local high frequency, then on the package, ultra high frequency. And always VCC and ground layers is a ultra high frequency capacity, it's a set of capacitance, which we get it. That's taken care in the stack up. Then we have got a ring of capacitors, like a chakravyuha, a ring of capacitors. Okay, so that's how we put a very good a constellation of capacitors. And many PDKs, they recommend you have to put a particular capacitor between a particular VCC and ground pin of a device, and you have to put it at the same location. That cannot be violated because they have done the simulation at the package level. They give a recommendation. Capacitor types 01005, 0201, 0402, 0603, 0805, 1210. As you move away from the package, near the package it will be 01005. Away from the package it will be 1210 capacitor. That's how it is. They tell exactly how many capacitors to put. People put a bank of capacitors. This still works actually. Next page, please. Design mitigation strategies. Now, what happens if we don't do this? There is a PDK recommendation, and then it is very attractive to remove a few capacitors and create space for some other component, or every capacitor will have a VCC ground fan out. If I remove two wires from the board, I get spacing to route the critical signals. So we may remove some capacitors, thinking why there are so many parallel capacitors. So we may remove some of them. Not we, but typically somebody may attempt to remove. So what happens if you remove that? Or even you move from the current location to some other location. A jitter response supply ripple greater than 5% can raise jitter up to 30% in high speed links if you don't put capacitors properly. Though we put the actual value, actual capacitor, if we don't put in the right location, it is as good as not keeping it there. So that's the scenario. BER degradation, bitter ratio, eye closure from droop hotspots, thermal stress, excess current flow, and current concentration, and EMI from unstable PDN. Supplier compliance gaps. Without explicit PA budget cases, vendors may underspec decoupling. So what happens is, we buy a very costly chip, we do the layout, and we violate the recommendations. We don't do the capacitor replacement properly, then the chip vendor is very happy to say that since you have not followed my requirement, I cannot guarantee HSIO performance. Now we are violating a risk. So that's how it is. And generally, people do the power distribution layout and then share with the vendor. They sometimes they review or sometimes they simulate and they give it back with recommendations. If there is any violation, they flag it. Next page, please. Yeah, another. I think only 3 more slides are there. We are on time almost. So here we are told in many OEMs and ODMs, especially signal integrity analysis and power integrity analysis was happening separately or sequentially. Now it has to happen almost in tandem. So I have shown there are signal integrity analysis in blue color and power PDN analysis in light green color. This has to happen, a co-simulation has to happen. Many standard EDA packages are allowing this to happen, but they have their own pricing and their own setup, but it is available in the market. So it's not a problem. So this has to happen. The PDN signal integrity analysis and PDN analysis. Here I have told it is a two coins with the same face. Generally, people say two faces of the same coin. Here, reverse analogy I did. I told same two. I told here two coins with the same face. So you have to do it. If you don't do it, it's gone. Okay, next page, please. Here, when we do co-simulation, I've just shown the difference between a PDN analysis and signal integrity analysis for a channel. On the extreme left, on the extreme east of the sheet, I have shown high-speed I/O channel model in the simulation, maybe pre-layout and post-layout. How we do, we have a driver, we have a receiver, we have wires, we have all sort of things. We look at the eye diagram. Then actual package is there. And then on the right side, we are doing PDN modeling and analysis. And nowadays, people are doing co-simulation, or at least they're using power-aware signal integrity analysis. So this has to be done. I think I can leave another 15-20 seconds on the screen if people want to concentrate, or when they're watching this, they can watch at their own leisure. But there is a lot of information in this, how it happens in tandem. Okay. Or sometimes what happens, the signal integrity analyst will not agree with a PDN analyst. They start conflicting with each other. Most of the times, the victim will be the actual layout designer and the product. So that if they show some recommendations, change this. If we change SIA, some recommendation, it may affect a PDN. If we change PDN something, it may affect SI. That's why I told it is a co-simulation. Okay, next page, please. Here are the similarities. Similarities between HSIO channel and PDN budget. Here the similarities are both HSIO channel length budget as the planning and the PDN planning in a server boards are fundamentally about distance and time driven margin. Your signal should reach in time, and your power also, whenever there's a depletion wave, the power should replenish within the such and such a time. So it is both time and distance. Allocation, each defines a maximum physical length over which losses or a droop can be tolerated before timing, jitter or reliability issues will they start raising their heads. In summary, both budgets translate electrical limits into spatial constraints. I was tempted to write physical constraints, but I told spatial because it is X, Y, and Z. All the three directions matter. Spatial constraints that must be simulated, and respected sign-off reviews. You have to do the simulation as well as in the sign-off, you have to review it again. Next page, please. The guidance, both budgets are spatial translations of electrical limits, both time and distance. Treat channel length budget and depletion length budget for the PDN as parallel audit items in a server board, even in DFM and DFR checklist. Express both in numeric class level terms, just an example. Less than 150 mm for a high-speed PCB at 125 Gbps is for the signal length versus less than 15 millivolts drop across a 20 mm plane. This goes hand in hand. Don't assume the planes are infinite. Actually, planes are finite. Integrate into simulation models, reviews, and supplier audits that can be validated by both the signal integrity analysis and power integrity analysis simultaneously. Next page, please.
Wow, I like this.
This is the depletion wave. Dynamics of a PDN depletion wave in power distribution network in 112 Gbps HSIO PCB design. It can happen in any board. Even it can happen in a 56 Gbps board also, but I'm obsessed with 112 Gbps. That I like that number. Okay. So this I will explain again when we go to next stuff.
Session.
So don't take power for granted. Power has got a peculiar characteristic of raising its ugly head when you require it the most. Either it will malfunction at the right location or it malfunction at the right time. So that's how it is. Okay, thanks.
Thank you, Mr. Ambaprasad, and thank you all for watching our show and supporting the show as always you guys do. And I would definitely request you to subscribe to our show, our channel, and as we have more subscription, the viewers will increase, and that will help our guest also to feel good about the show and about their activity. So as I mentioned that Global Electronics is engaged every week in bringing new topic to you all. And if you want to participate, if you want to be part of this talk show, please do contact us. And the email to contact is globalelectronics1234@gmail.com. So with that, Mr. Ambaprasad, thank you very much again for your continued support in this channel and contributing your wealth of knowledge, your wealth of experience to educate our other electronics community members. With that said, everyone, thank you very much. Have a wonderful weekend, and we will see you next week at the same time with yet another topic with your host Raju Kulkarni, and we will come back with another topic. Thank you very much.
Power.
Thank
Good
you very
speed
much.
and good power.
Yeah, thank you.
Thanks.